by Taiji Suzuki from the University of Tokyo.
Thank you for the introduction. My name is Taiji Suzuki. I'm from the University of Tokyo, Japan. This is a collaboration with Masashi Sugiyama, who is in Tokyo Institute of Technology in Japan. So, in machine learning, the following question: what is an effective regularization? What is a good regularization in terms of the statistical performance? Is an important and fundamental question. So, in this talk, I'm going to discuss this question and give one possible answer to this question. In particular, we are interested in the following question: is L1 regularization the best, or should we use other regularization to achieve a good performance? So in this talk, we are going to discuss these issues in the framework of multiple kernel learning, MKL. Okay. So in particular, we focus on the non-parametric regression. So the non-parametric regression is a basic concept of machine learning. So it is important to investigate this situation. So in particular, we investigate the non-parametric regression estimated by multiple kernel learning. Okay, so what is multiple kernel learning? So now I'm going to explain an important example of a multiple kernel learning, the sparse additive model. So suppose that the input vector x is high dimensional, and the input vector x is a concatenation of components x1, x2, and so on. And it is high dimensional. And then we put a nonlinear function on each component, like f1, f2, and all of them are nonlinear functions. And then we sum up these functions as a sum of fm to obtain a function that takes entire vector as an input. So the terminology sparse in the sparse additive models comes from the fact that a lot of functions fj is zero, a constant function 0. So in that sense, the sparse additive model is sparse. So here, because each function fj is nonlinear and that is estimated in a non-parametric way, so the sparse additive model is flexible. And moreover, because of the sparsity, the sparse additive model can be applied to a high dimensional data. So flexible and high dimensional. Now, if we assume that each function fj is linear, like f1 x1 is beta 1 x1, like this, then the sparse additive model is reduced to a sparse linear model. And that can be estimated by Russell and some other sparse linear estimation methods. So now we are back to the sparse additive model. The standard approach in the kernel methods to estimate the sparse additive model is to assume each function fj is an element of RKGS. So we assume that each function is an element of RKGS. Now, for example, f1 is an h1 and f2 is in h2. Here, hn is the nth RKGS. We have a lot of RKGS. Now, the multiple kernel learning is more general framework than sparse additive model. In the sparse additive model, we assume the function fn takes the nth component as an input. But in the multiple kernel learning, so each function fn can take the entire vector x as an input. So, okay. Then in the multiple kernel learning, we also fit the sum of functions fn to data. So here again, we assume that each function fn is an element of RKGS. Here hn is the nth RKGS, and we suppose we have a lot of RKGS, the reproducing kernel qubit spaces. So how do you estimate this kind of function? The most naive approach is to minimize the loss function. So here we consider the regression function, so we employ the squared loss for loss function. So, but just minimizing the loss function leads to overfitting. So we need to add a regression term to avoid overfitting. So there are a number of candidates for regularization terms. In the original multiple kernel learning, they employed L1 regularization for the regularization term. The L1 regularization is the sum of RKGS norms of each component of fn. So this is analogous to the standard L1 norm in the finite dimensional Euclidean space. So an important property of L1 regularization is that L1 regularization generate sparse estimators. Another possibility is L2 regularization. The L2 regularization is the sum of the squares of RHS norms of Fn. But it is not appropriate to utilize L2 regularization in a high-gain generator because L2 regularization does not produce sparse solution. So it is more natural to consider the elastic net regularization. That is a mixture of L1 and L2. So the elastic net possesses the properties of both L1 and L2. In this presentation, we focus on these two regularization, L1 and elastic net. Now, we are interested in which one is preferred in terms of statistical performance, L1 or elastic net. To answer this question, I'm going to show two numerical examples that motivates our theoretical analysis. The first example is the computation task, Caltech 101 dataset. The graph shows the classification accuracy. The lower is better. From left to right, the regularization is changed from L1 to L2. The horizontal axis is the mixing rate of L1 and L2 in the elastic net regularization. So you can see that the best performance, the star shape symbol, is achieved by the elastic net regularization, not L1. And importantly, regularization is outperformed by our regularization. That is an important point. Another example is borrowed from a paper by Cortex et al. In 2009. They also claimed that the regularization between L1 and L2 performs. Importantly, they also claimed that L1 regularization does not perform example. So, in these two examples, we have observed that L1 regularization does not necessarily perform well. That is an important point here. So, the question here is the question: why doesn't L1 regularization necessarily perform well? This is the main theme of this presentation. So, in this presentation, we are going to give one possible answer to this question. Okay. So, to answer this question, we are going to analyze the generalization error of estimates. So we employ L2 error as a generalization error. The L2 error is the L2 distance between the true function F star and the estimated function F star. So we denote by F star the true function. The true function F star x is the conditional expectation of y given x. So in other words, the output sample yi is x star xi plus a noise I. So noise I has been 0. And we assume that the true function f star can be decomposed into the sum of the function f star. The f star m is the nth component of the true function and is an element of RHS. Hm is the RHS. Now we also assume that the true function f star is sparse, in a sense that a lot of f star m, a lot of components f star m are. So here we introduce a number d. D is the number of non-zero component of the true function. D is the number of m for which f star m is not equal to 0. So the meaning of the sparsity is that the number d is much smaller than the number of m. M is the number of RHS we have. Okay, now we are going to analysis. Before we are going to analysis, I have a brief remark. This is just a remark. As I have presented in the previous slide, L1 and elastic net MKL are defined by these formulations. But in our theoretical analysis, we add an additional term, FMM. FMM is an empirical L2 norm. We are an empirical L2 norm on the regularization terms. So this is because with this term, we can show that MKL can achieve the optimal learning rate. So theoretically, this term is important. So the basic structure is the same as in the previous slide. So now I'm going to the theoretical analysis. So there has been a several existing works about the statistical performance of multiple kernel. These are examples. So remind you that D is the number of non-zero components of the true function. The most relevant work was given by Korczynski and Yuan in 2010. They showed the convergence rate of L1 MKL. According to the research, the error bound of the L1 MKL is given by D times n to the power of minus 1 over 1 plus s. Here, the parameter s, this is very small, so but here is a parameter s. S is a parameter that represents the complexity of the model. The complexity of RPS will be explained later. So, it is noted n to the power of minus 1 over 1 plus s this term is the minimax optimal rate for a single kernel run. So the running has a convergence rate that is d times the optimal rate of the single kernel run. And actually, it was shown that this is a minimax optimal rate by Sugiyama in U. Okay. But the problem of the existing research is that there has been no comparison between L1 and elastic net. There has been no discussion. So what kind of regularization is good? So based on this concern, I find this is as follows. The smoothness of the true function F star affects which of L1 and elastic net is preferred. The smoothness of the true function determines what kind of regularization is preferred. As a consequence, we will show that if the true function is not smooth, L1 is better. And if the true function is sufficiently smooth, elastic net is good. So, smoothness. The smoothness is an important notion. So, what is the smoothness? So, how to define the smoothness? So, next slide, this one, I'm going to define the smoothness rigorously. So, we showed parameter Q, that is the relation between 0 and 1. That represents the smoothness of the true function. The Q represents the smoothness of the true function. Now, define a self-adjoint operator sigma m that is mapped from HM to HM. HM is the mth RHS. That is defined by sigma m G is the kernel function Km and the function Gm. Here, the Km is the kernel function corresponding to the RHS HM. So, because sigma m gives a convolution, sigma m can be seen as a smoothing operator. Okay, sigma m is a smoothing operator, so they make Gm smooth. So the smoothing operator Q, smoothing parameter Q. So we assume there is smoothness parameter Q, and element of G for m, based on G for m, such that the nth component of the true function f star n is expressed by the sigma n to the power of q over 2 times G star n. Okay. Now, if equal 0, this term corresponding to the smoothing operator sigma m is identity. This is identity. So we have nothing on the true function. But as q increases, the influence of this term, the influence of the smoothing operator becomes large. In that sense, the function f star n becomes large as q becomes large. So the larger q is, the smoother f. So that is the definition of the q. Okay. Next, there is another important parameter, S. S is a parameter that represents the complexity of RHS. So now, by Masa's theorem, the kernel function Km, the kernel function corresponding to the nth RHS Hm, can be decomposed into eigenvalue and eigenfunctions. The parameter S defines the decreasing rate of eigenvalue. Now we assume that the eigenvalues mu Ln is ordered in the decreasing order. Then S determines the decreasing order eigenvalues. So if S is small, the decreasing rate of eigenvalue is fast, like this. And if S is large, the decreasing rate of eigenvalue is slow. So since the eigenvalue determines the structure of the inner product in RHS. So if eigenvalue decreases quickly, the situation is more like finite dimensional situation. So in that sense, the RHS is simple. On the other hand, if the decreasing rate of eigenvalues is slow, the situation is more like infinite dimensional. So in that sense, the terminal S determines the complexity of the RHS. So the larger S is, the more complex RHS needs. Based on these parameters, our results are given by this. This is the main result of our work. The theorem shows that the error bounds of L1 and elastic net NKL. So these are complicated. So you see that here the parameter Q is moving parameter Q in the convergence rate. So we can show that as the Q becomes large, the convergence rate becomes fast. So in that sense, our bound is more general than existing bound. Another important point is our bound involves the norm of the fields, the R1 F star and R2 G star. R1 F star is defined by the sum of RHS norms of F star n. Then R2 G star is the L2 norm of the RHS norm of G star m. The relation between F star m and G star m is given by this in the previous slides. Okay, these are complicated, so now we are going to compare these two bounds and then discuss which is better. Now, they are thickness regularization. So, as said, the smoother the function is, the larger Q is, the faster the convergence rate is. So that means the elastic net regularization can make use of the smoothness of the two functions. The elastic net regularization has an activity to smoothness of the two functions. Note that we don't know a priori the smoothness of our if we apply the cross validation, we achieve this convergence rate. So the elastic net has an adaptivity. Now, on the other hand, the convergence rate of L1 MKL is given by this. You see that there is no dependency on Q, the smoothest parameter Q. This has a milder dependency on D than elastic net when Q is 0. So remember that D is the number of non-zero components of the tools. And if Q equals 0, then the convergence rate of elastic net MKL is given by this. And if we look at the term into D, we can find that this term is smaller than that in elastic net MKL. So this reflects the fact that L1 regularization produces a sparse solution. In that sense, L1 MKL make use of the sparseness of the estimators. So here is a trade-off between the sparseness and the smoothness. If the true function is sufficiently smooth, elastic net regularization is faster than L1 regularization. And if the true function is not smooth, regularization is more accurate than elastic net. And here is the trade-off. This is the main consequence of our main result. Okay. Finally, we are going to compare our bound and with the existing bound. The existing bound is given by like this, and our bound is given like this. The main difference is that our bound involves the norm of the true function R1 F star. If R1 F star is D, the norm of the true function is D. This situation is that the true function is on the corner of the L infinity normal ball with radius 1. Okay. In this case, both rates are same. So in that case, our bound recovers the existing bound. So our bound is more general than existing bound. On the other hand, if the norm of the true function R1 F star is 1, the constant, and this situation is that the true function is on the corner on the edge of the L1 normal with radius 1. In this situation, our bound is d to the power of 2s over 1 plus s times tighter than existing bound. So our bound is always tighter than existing bound. In fact, our bound achieves the minimum optimal rate on L1 normal, while existing bound achieves the this discussion of minimax optimal rate is a bit complicated, so I skipped this. So finally, I gave a numerical experiment. The numerical experiment also shows that if the true function is not smooth, L1 regularization is better than elastic net. And on the other hand, if the true function is sufficiently smooth, elastic net is better than L1. Okay, so the numerical experiment also support our okay, now I'm going to the conclusion. So we have observed that the smoothness of the true function affects both of L1 and the elastic interval. So the smoothness, the true function gives one kind of regularization. And there is a failure between the smoothness and smoothness. If the true function is smooth, elastic better than one. Otherwise, it is better than elastic net. So more technically, our rate involves the smoothness parameter Q and then the norm of the true function R1 is turned out to G star. So as a consequence, we get balance than it is balance. Another work I picked is that we derive the max optimal rate from LP normable with the parameter Q, an extension of existing results. Okay, thank you.
Any questions? No?
So you had this smoothness parameter S, the spectrum parameter.
Yep.
It was like a polynomial decay rate. So I was wondering for Gaussian kernels, I think the decay is exponential, right? So they all look the same to you, or?
I think so. But, the analysis is difficult, but I think intuitively, as in the in the polynomial case, in the Gaussian case, we can also show this kind of discounting or bound. Yeah. Thank you.
And for the second question. Actually,
So do I understand correctly that the right proportion between L1 and L2 depends on the smoothness of the class?
Yes, that's right. I skipped that kind of things, but the true parameter, the best parameter depends on S and Q and the norm of the true function, and we cannot know that a priori. So we apply the cross validation, then we obtain the best tuning parameters.
Is there also a limit statement for how smooth does the function actually have to be such that L2 becomes the right norm?
Pardon?
Do you also have can you have given a tuition for how smooth the function has to be such that L2 becomes the right norm, so that you don't need that one anymore?
So you mean the phase transition?
Yeah.
Yeah. But it is quantitative phase transition, so it is hard to say qualitatively. So it's hard to say intuitively. Okay.
And I think we go again.